Okay, so I've said to a couple of people that where we are today came out of us coming to that meeting 2 years ago. Up until that point, I'd been working on a technology which in our sort of microbiology world was fairly niche. It had been developed for detecting TB in human sputum. And it was developed 20 years ago. And around about that time, a little new method came onto the scene called PCR. And kind of nobody in a clinical setting wanted alternative ways to find TB, because in a clinical setting, you'll do it with a molecular test, you'll do PCR. So this technology had sort of kicked around, and then the company there was a spin-out company who developed it from the University of Nottingham, and they asked us to start looking at veterinary applications. And we had totally focused on Johne's disease, and many of you in the room will know the issues with paratuberculosis and Johne's disease. So that's what I came to talk about. But the technology started off as a test for human TB. It works exactly the same way with paratuberculosis. So we know it will work with bovine TB. And really, up until that point, we had been very, very cautious about getting into the world of veterinary bovine TB detection. And part of that was because it is a very controversial subject. It is very structured. It is embedded in law. It is actually a very difficult place to go. But what we realised 2 years ago was that there was a niche application for what we were doing that would maybe provide a new service for cheesemakers in particular that would be of value. And from that time, we've spent 2 years working and developing on methods. And what I'm going or what Ben is going to, he's going to be the good cop. Bronwyn has given me the bad cop job, because I'm going to tell you how bad TB is and how awful it is and why we haven't got an answer. Okay, so I get you the bad news, and then, Ben over there, who's been working on the project for 4 years now, is going to do the good news. And at that point, we need crowd participation. I've got Jamie ready to drum you up and get you all excited, but we'll come to that later. Right, so what I'm going to do is a little bit of a review. It's a little bit historical. You may know a lot of this. You will certainly recognise some of the graphs. But what I want to do is to sort of set it in the context of why we think the current methods of testing are part of the problem and what we can offer as an alternative. Right. Okay, so here's real history, okay? So we know that back in the 1930s, okay, it was estimated that about 40% of dairy cows in the UK were infected with M. bovis. So the reason for that was, well, there wasn't any control, but one of the problems were they were kept near large cities as a source of fresh milk for people living in the cities. They were often in close confinement, kept in sheds that were poorly ventilated, ideal places for bovine TB to pass around, and there was no screening and no control. So the disease progressed in most cases from the lungs to the other organs, including the udder, so the milk was contaminated. And most of the milk was drunk raw, so M. bovis was spreading to humans, and that's when our whole concern over this organism sort of came to the fore. So back in the mid-40s, we're looking at 50,000 new cases of bovine TB per annum in the UK population. Okay, so this was an epidemic. So, mid-1930s, the pasteurisation technology started to come to the fore. So people started to have pasteurised milk. And then in 1950, the TB eradication programme, through routine testing of animals, doing the skin test and culling, started to happen. And we got a graph. Okay, so in the graph we can see 1962, and the blue line there that's the rest of England and Wales. I just point out that this is the southwest. The southwest has always, it's not a new problem in the southwest, it has always had a higher incidence. And this is a percentage of herds that were found to be affected. So you can see it comes down nicely across, even though we've got some fluctuation, there's a nice downward trend. So by 1979, at the end of this, they felt that eradication was going to be possible. It's all under control. Okay. So if you look at the human population at the same time, okay, so we are down to 5,000 cases per annum, all right? And if you look at the age distribution of those, many of those people are elderly. It's reactive TB. People who were exposed in childhood, it lays dormant for long periods of time and comes back. And you can see, if you look at the data in the chart, from 1977 there, going forward, the numbers decline. 1990, 31 new cases of bovine TB per annum. It kind of stays there. That's what we're looking at now at the current time. So we're looking at a problem in the human population coming under control. But then, of course, 1980s, and the graph takes that characteristic upward trend, okay, nationally, but in the southwest in particular. Now, this graph here, this data, finishes in 1996, and again, this is looking at herd prevalence, but I found this data that started in 1996, and this is the number of cattle slaughtered due to bovine TB in the UK, and you can see we're on a nice upward trend, and these are in the thousands. So 2008, we're looking at 40,000 cattle slaughtered. So we're back to the point we were back in the 1960s, where the disease is out of control. Now, interestingly, think about the human cases. It's still 1 to 1.5% of all human TB cases are bovine TB. So our ACMSF, which is our Microbiology Quality Advisory Committee for the Food Standards Agency, they concluded that the food vehicle has been removed. So even though we have the incidence in the cattle that we had back in the early days with high incidence, because the food vehicle through pasteurisation has been removed, then this is why the cases in the human population stay low. And in fact, what we're seeing is mostly the new cases are often opportunistic infections of patients with AIDS. So it's not sort of the general population. Okay, so let's talk about why this has happened. So again, you're probably all very familiar with this. So the skin test. We have the single intradermal comparative cervical tuberculin skin test, okay? And what it's looking for is the immune response of the animal to exposure. It's asking the question, has that animal encountered M. bovis and raised an immune response to it? Okay? And it's done comparatively because there are an awful lot of other mycobacteria out there. So there is an avian tuberculin from Mycobacterium avium, which is normally an bird pathogen, and they use the two different tuberculins to ask the question, if this animal is raising a response to mycobacteria, is it specific to bovis? Because the reaction to the bovis is stronger than the reaction to the avium. Okay, so it's not general mycobacteria, it is specifically bovis. So using those two minimises false positive results. But although it increases specificity, it has been recognised that by using that particular form of the test, it reduces the sensitivity to 80 to 90%. So 80 to 90% found is 40,000 cattle. Let's be generous, let's say it's 90. That means there are 4,000 cattle which are missed. If we're 80%, that's 8,000 cattle that are missed. If it's in some of the estimates, which is nearer 40 to 50 to 60% I've seen, we're talking about an awful lot of cattle going undiagnosed. So this is our reservoir, this is our problem. That it's not that the skin test isn't effective, it's just that it's like vaccinating a population. You need to get them all. You need to get the last ones. Getting the last ones are difficult. And because the last ones are hidden, they're staying in the population and they're spreading disease. So it is this intrinsic problem. And the other problem, they all recognise it is relatively qualitative when you're doing this test. It's a skin test. So what you're looking at is a difference in the two lumps of 4 millimetres, that's a reactor. If you get a difference of 2 millimetres, but you've had TB in your herd, you're also a reactor. If it's 1.9 millimetres, you are not a reactor. You're intermediate, okay? It's a bit of a fine line of a cut-off. So in an ordinary herd, 1 to 3 millimetres is considered inconclusive. So you do another test, and if it's another 1 to 3 millimetres on the second test, it's probably infected, so we get rid of it. If it goes down a bit, it's probably okay, you leave it. So this is the problem. It's a very difficult interpretation of the data. So, all right, so that's the problem. Now, Bromley asked me to look at what is it in farm management that makes you at risk for a herd breakdown. Okay, what is it about we're doing in sort of animal practices? Now, I'm not going to mention the B word at all. All right? Just because I know it will probably just end the debate then, we'll just have an argument. All right, so the B word's not going to come up. I've got one reference to wildlife, all right? But apart from that, okay. Right, so if you look at all of the studies, so what I've been doing is going through the literature and looking at everybody's studies of everything and saying, what is it that consistently is found? It doesn't matter if you were focusing on badgers, it doesn't matter if you were focusing on the test or what you used. If you look at the risk factor management, what comes up, what's top of the hit? And top of the hit is cattle movement, every single time. Okay, so if you want to predict whether or not you're going to get a herd breakdown, it's cattle movements. We've got our reservoir. Is this surprising? Okay, so you're bringing a new animal into a herd. If it's unlucky on your Russian roulette of the 8,000, whatever it is out there that's infected, this is what's going on. So we've got this problem with the numbers out there. Another interesting fact for you, if you look at the statistics from DEFRA and ask the question for all of those non-reactors that go to slaughter, where on meat inspection they have found a lesion, 75% of those culture bovine TB. So it's not just a probability number, that 4,000, they're finding them, okay? So there is a big reservoir of undiagnosed TB in our cattle population. So it is the most commonly identified risk factor is bringing in new stock. Okay. The size of the herd is another one that comes up time and time again. So the risk of any one animal becoming a reactor increases in proportion to the size of the herd. Number of reactors per herd increases as the size of the herd increases. Now, if you think about this in terms of exposure, that's not surprising. You've got more cows to interact with, so you may get more cow-to-cow spread. You've got larger farms, so there is more neighbours, including wildlife. Okay, so my one mention. Okay, that's it. All right. So yeah, bigger numbers of animals in one place, all mixing together, you may get more spread of disease. Yeah, it's not rocket science. But what's interesting, if you look at the table at the bottom, is what's happened to herd numbers in the UK. So we're looking at 1999 to 2009 in this table. If you look at the trend, this carries on going upwards. And you go from 80 average herd size in 99 to 113, and so herds are gradually getting bigger and bigger, and economics is driving that. It is more economic to have a larger group of animals to look after. Okay. Another one that comes up is production, stress, and body condition. So high levels of milk production associated with an increase of any one animal becoming a reactor, decreased body condition, so as my friend who's a vet describes it, these animals are like greyhounds. They're running on lean, okay, a lot of the time. It's the decreased body condition score is also increase a risk of a positive test. And what are we doing to our cattle in the UK? This graph, okay, the red line is the average size of the national dairy herd in the UK. So we're coming down. And that line is the production units per animal. From 1995, we're at 54,000 litres per cow per annum. In 2012, we're at 7,400 litres per cow per annum. It's a risk. Okay. Being a dairy herd is a risk. Okay? So, part of this, they believe, is related to that increasing the production yield, shifting over to from traditional British breeds to a higher proportion of high-yielding breeds. There's an older age of cattle in those herds, so those animals last longer, so increased risk of exposure because they're around longer. They also have, as they get older, a lower cell-mediated immunity response. So the cell-mediated response you need to fight off infection goes down. And you have an increased chance of reactivation of latent infection. Animals that were exposed, it's gone latent and comes back later, just like it does in humans. So all of those means that just being a dairy herd increases the risk of a breakdown. Genetics. Okay, so we've already mentioned this idea of a shift in the breeds, but there has been quite a lot of concern about the whole idea of using a test and cull policy and what that's doing, driving the genetics of the national herd. So there is likely to be a herited part to either resistance or susceptibility to infection. We see this in many other mycobacterial diseases. There are alleles that we see that mean people are more likely to get full-blown TB, for instance, in the human population. So it's not surprising to think that might also work in cattle populations. We know we need this strong cell-mediated immune response to control infection. What do we test on? We test on a nice big lump, a really strong cell-mediated response. And what do we do to those cattle? We cull them. Okay, right. So the test and cull may be selecting out for animals that maybe are less able to raise that response. Okay, so that was the question that was asked. Fabulous paper last year, 2013. And this group, Amos is the lead author, but there's a genetic predisposition to pass the test. So what they found is that if you look at the cow populations, there's a marker gene called NRA111. You don't need to know what it is. It's a gene. They found out they can track it in cow populations, and there's variability in that gene. One particular allele, called 22, is relatively common. And if you have that genotype, if you are that one, you are more likely to be a non-reactor to the skin test. So it looks like they did a study, the control for age and the breed. Those 22 type cattle react less strongly, so they're less likely to be picked up. So we are selecting for the ones in the population that are likely to be missed in the test. What do you think that's doing to our 80 to 90% value on sensitivity? It's going to push it down. Okay, and I wanted to start off to finish with a really bad news story. This is going to cheer you all up. No end, this one. Okay, so do we care? We've got this latent infection in the population. The humans aren't getting it, all right? Is there really a risk to human health? Well, the bad news is, in this paper, and there are older reports, there's some lovely studies have come out of India where you don't do lots of PCR, you do lots of culture. They are the best microbiologists in India. And they culture, do lots of culture work. And in this study, though, again, what they found was 6 out of 8 milk samples from non-reactors were either PCR or culture positive. Not just PCR positive, culture positive. Okay? And you can find other reports in the literature that does this. This was just a nice new one, 2013. So we know that the non-reactors, it's not just a case of latent TB, it is getting into milk as well. Okay, so what can we do? Well, the AVLHA is working on a vaccine, okay? They need a vaccine that doesn't interfere with the skin test. This is part of the European legislation and the current framework that we have to work within. If we want TB-free status, we have to be able to carry out the skin test. Irrespective of what it's telling us, we have to be able to do it. Okay, so the AVLHA are working very hard on trying to find a vaccine that will protect the animals but still allow the skin test to work. So that's one answer, but we know that even if we get that, there's going to be a 10-year lead-in before we can start using it, because it takes that long to get through the changes in Europe. Okay, what about go for broke? Give up our TB-free status and vaccinate all the cattle. Now, the argument that's put against that is that it only gives you 80 to 90% coverage, so you'd leave all these animals in the population infected. I'm going, yeah? What's different? We would be in the same position as we are now, but it's a strategy that might lead to eradication, rather than a strategy that might actually be exacerbating the problem. So it's thought. There is a group out on the web, I think it's called Rethink TB. Their figures say we spend 100 million trying to control BTB using test and cull. Our exports that are dependent on live animals, which is the only bit that's affected of our export, is 3.3 million. So we're protecting 3.3 million of agricultural imports with 100 million. I can see their argument. Okay, so that's all long-term problems, politics, and things that are not going to happen overnight. So, is there good news? Can we have a new test to detect the organism in blood? So, this was the paper. It's Ben's paper from last year, 2013. And here we described our new method for finding paratuberculosis in blood in 48 hours. This has caused quite a stir in the para-TB industry. So, this is the phage amplification assay. I'm not going to tell you, those of you here last time I told you how it worked. We're not going to go into the details of that now because we're going to focus on the science, we're going to focus on something else. And Ben's going to talk a little bit more about this. You've got a sort of a brief outline of it. But what I just wanted to point out to you was that this assay means we took samples, we did things with phage, which Ben will talk about, and then we had agar plates at the end in which we saw the plaques, we saw these zones of clearing, and that told me that mycobacteria were there. But actually, what he's done very cleverly is to invent what we're modestly calling the Swift patent method, because his name's Ben Swift, okay? And the University of Nottingham have just patented this, and we've turned all of that test into a 1-tube, 5-hour test. So we've moved on in 2 years, I can say. We are now away from the plates, and we are getting to the point where we can have a high throughput, lots of tests possible, which is, with plates, it is quite difficult to do lots and lots of tests. So we are slowly moving towards a blood-based diagnostics. And the good thing is, it's completely compatible with any vaccine you want to use. It doesn't matter which one you use, because we are not looking for an immune response, we're looking for the bug. So we can tell if you're infected compared to vaccinated. Right, I think that is all of me. I think we're going to have Ben first. Right, so, okay, that's where we've sort of progressed some perspective, why we're doing what we're doing, but baby steps. This time 2 years ago, everyone asked me, can I have it tomorrow? And I went, no. But where we've got furthest is with our developing our milk test, and Ben's going to introduce you to that now.
Hello, so I'm the good guy, apparently. So I'll just go through a bit more about bacteriophage and a bit more about what we've tested in the lab. I mean, a lot of what Cath said before was with para-TB, and it's good to drum home as the parallels is what we can do with para-TB is exactly the same as what we can do with bovine TB. So I'll go through that as well. It's just show that proof of principle, this is what we can do. Because I was asked a couple of times last night, is this test ready? Can we use it? It's like, yes, we can show you that we've done it lots of times. So I'll just go through some of those. So bacteriophage. So some of you might be familiar with bacteriophage. Some of them might not be your friends. I love bacteriophage, but if you've got them in a starter culture, they can be quite a problem. A little bit of history for you. So bacteriophage are viruses. But they specifically infect bacteria. So they're not going to infect humans, they're not going to infect your cows, you're not going to infect anyone else. They only infect bacteria. They were independently discovered by 2 scientists, 2 years apart. And you've seen that picture before. It was basically you'll get these zones of clearing on a plate. So you get a lawn of bacteria, and if you've got a bacteriophage in here, they'll burst open those cells and they'll form these zones of clearing. The reason they're called bacteriophage is because both these agents have the ability to eat bacterial cells. So phage means to eat, so it's bacteria eater. So I like them. I think they're quite nice. I know some of you might not. So bacteriophage. So like all viruses, they have a specific host rate. So the phage you might have encountered, maybe lactophage and whatnot, we don't use any of those. We use a mycobacteriophage. So they infect only mycobacteria, and they infect all mycobacteria. So when we talk about paratuberculosis, that's why our phage can infect paratuberculosis, and it can infect tuberculosis or bovine tuberculosis. They bind to the structure on the cell surface, and very commonly, the majority of phage have a tail-like structure, and this is what they use to inject into their cell. So this is one of the most common moonlander phage you'll see. So you'll see you've got a head here and you've got a tail, and you've got these little legs here which they'll land, so they'll find the cell on the cell surface. This is quite a good image of a phage actually injecting. So you can see here the tail is injected, so that will inject its DNA into their target cell and take over the machinery and start replicating. And it's just the bacteria. So this is how the virus works. And majority of the virus we use doesn't have all these contractile. It has a long tail, but the principle is the same. So why do we use phage? So again, 2 years ago, Cath will probably have told you why we use phage. They're really, really quick. So what we get basically is our mycobacteriophage can replicate inside the host cell and produce up to 50 phage particles per infection. So not sure microbiology-wise if you know how fast TB grows, but it takes ages to grow. And so when I was doing my PhD with para-TB, you can wait up to 16 weeks to form a colony on plate. So if you're looking for that as a diagnostic, it's pretty pants if you're waiting 4 weeks for TB. And for TB, you can take up to 8 weeks. So you've got two months of waiting around to see if there's something going to grow or not. So the reason we use phage is because the phage, basically, within a couple of replications, you can get up to 10 to 9 phage particles out of cells. And if you've got just a cell growing, it will take a long time, a lot of replications, just to get up to a 10 to the 2 sensitivity. So it takes a long time to detect them. Using phage indirectly, the phage will infect, they'll replicate really quickly. I mean, you've seen with the old assay it will take 24 hours. With the new assay, it will take 5 hours, and they'll burst out, and we can indirectly detect these phage replication. What is also very key with this, so unlike the PCR test, which will detect viable and non-viable cells, because DNA is going to be there regardless, these phage will only grow, and they'll only burst out from a viable cell. So we're only looking for these live cells. So that's really important, because that is a direct comparison to culture. So instead of waiting the long weeks that you'd have for culture, we're going to get these in now 5 hours, we're getting a viable result. So the rapid plaque BTB assay. So, yeah, sorry. So the test basically, you've seen the diagram before, the phage will go and infect the cells and then they'll lyse out. So what's novel about this 5-hour test is what we use the phage for is basically a novel DNA release mechanism. So instead of having to heat up a sample or break open the cell wall, the phage that have evolved for a long, long time to infect and to burst out the cells, we just use what they can do, and they can do that within hours. So what we do, we infect them with phage, that will release the DNA, and then we simply use a PCR at the end to identify the cell detected. And this PCR is routine, it's robust, it's validated, and very sensitive. So we can basically use our phage, they'll release DNA, and they'll only release the DNA from the viable cells, and then we can detect it. If you put on a quantitative PCR on the end, we can get numbers out there, so we can have an idea of how many cells that we're detecting in our samples. And this is just an example. You can see here, that once was a cell, the phage had burst out, and you can see what happens. There's a big lysis event, and your DNA is exposed. And then you can get a band on a gel, and that'll say, yes, no, there was bovine TB in a sample. So it's a really, really neat, really nice way, really quick way of getting your viable detection of TB from a sample. So, like I was saying before, this was all done with paratuberculosis and in milk. But like I said, everything is in parallel. So anything we do para-TB, we can do with TB. So we've done this to death now. We've done quite a lot of work with detecting para-TB in milk. This is just an example of some of the data we've done. So this is just a simple graph showing how reproducible the assay is. So when you can take a sample, you have 2 samples from the same animal, you can plot them on a graph and you get good reproducibility of what we're getting, and you get good sensitivity. One of the best, good examples of what we've done lately, well, I say we've done, Cath's got a new PhD student, so I'll go through some of these timelines and stuff like that. So I'm looking smug because I didn't have to do any of the work. Basically, what Azara did, so the new PhD student, she collected 100 samples, so all pasteurised milk. So Cath had the bright idea to bribe people to bring in a pint of milk for a Kit Kat. They'll bring them in, and we'll test them to see if we can find any para-TB in there. So we included commercial retailers, doorstep providers. We took a 50 ml sample from that milk, centrifuged it, washed a pellet, and ran it in the phage assay. So the important thing here with this processing is it's routine processing. It's what's done pretty much every day when you go to the milk testing labs. We wanted to make sure that our testing could be applied pretty easily to any other milk testing. So just centrifugation, simple washing steps, and do the phage assay. And what we found, which was interesting, so the original study that was done 2004, was it? 2002 showed, and this was done by culture, so they were looking for the viable cells. What they found was that 2% of all retail pasteurised milk contained a viable MAP. So what we managed to do, or I say we again, this is Zara, within 6 days, bless her, processed 100 samples on our own. We managed to find 28% of the samples were positive for viable MAP in the milk, and this was all done in 6 days. So this is how fast we can do it. One person just started getting all our milk samples, bribing people with Kit Kats. We can find that 28% sample actually did have viable MAP in there. And this is using the phage assay. And this 6 days collection was basically, the samples weren't collected all at once, they were collected over a set amount of time and processed through, because she's only one person. And I don't know why I wasn't helping, I don't know. Must have felt too big for my boots. But it's just an example about how fast we can do quite a lot of samples. We can test them all for para-TB, and we can get the results really quickly. And so we're getting quite a lot of interest from government organisations, we say, about this and the potential for the phage assay to detect MAP. So again, this all leads into TB. If we can get one PhD student, give her 100 samples, and in 6 days detect any mycobacteria in the milk, this is the way we're going. How this relates to TB and how hopefully it relates to you guys is, what I'm doing is looking for TB in raw milk. So during my PhD, I was looking mainly at para-TB. 2 years ago, Cath came here talking about TB. We started looking to ask the questions about TB in milk. So in the lab, we've done a lot of proof of principle. We know that we can detect TB in BCG in milk. We can spike samples in. Now we want to know if we can detect it in actual clinical samples. So this is what the application we're looking for. So with your... Sorry, you have to click that button a few times. One back. One more back again, sorry. Yep, that's perfect. So we know a problem that you potentially do have, especially if you're in an endemic area. You can have your skin test. So cows on your herd, dairy cows on your herd, could have a skin test and it'll be negative. You're happy to use all that milk and you can make your cheese. And then a year later, you can have another test and it'll be negative. So you're happy with all that cheese, should be fine. There's no potential for there to be any bovine TB in that milk. What we don't know is if you have a negative skin test in the early cow, and then do we get a breakdown? What happens to your milk? So, yeah. So we don't know which batches of used cheese are safe. So we don't know in that year gap, when has that cow encountered TB? When is the skin test? Is the cow shedding any TB into the milk? Which one of those batches of milk to make that cheese has potentially become contaminated? And I know that's a big problem for you, because which batch do you have to destroy all that milk within that year? Do you have to destroy just a certain batch? That's the questions that you need to ask, and you can't really answer them. So the idea for us is, when did the cows get TB? So the idea for us is we want to be able to answer that question for you. So we have a test that we can do within a day. We have a test that's really quick. We have a test that will give us a bit of idea about numbers and how much TB is in a sample.